Ready? Okay. Welcome, everyone, to the Unitarian Church of Los Alamos. Whoever you are, wherever you are on life's journey, whatever you believe and whomever you love, you're welcome here. My name is James Carroll. This is our forum. It's a little different than what you usually see me do. I usually do the comparative religion or the biblical class. But those who don't know me, my PhD was about 10 years ago from Brigham Young University in machine learning. And my research was on part of speech tagging for ancient religious texts. So I kind of combined my interest in religion and artificial intelligence. My goal originally was to teach religion, and then I had a faith transition, I guess, and I ended up here at the lab doing research in computer radiography, image analysis, which was sort of related, but that meant I was out of the loop on artificial intelligence for about 10 years. And during those 10 years, everything changed. And in the last little while, I've started doing some research again in artificial intelligence. And it's been exciting to get back into one of my original loves and also to look at the field and figure out how it's changed. I know this topic is interesting to everyone right now, specifically because of ChatGPT and all the AI art and the other stuff that's happening in the world. It feels like artificial intelligence really has come of age and has begun to change the world. And because of that, it's a reasonable time to look at it and to take another look at it and what it is and where we've come from and what we're doing when we're here. So to begin, though, I think we need to just ask the question. I know a lot of the questions we're going to want to ask about artificial intelligence, like, can a computer think? Is a computer intelligent? Does a computer have consciousness? Depends on defining things like think, intelligence, consciousness. And we don't know how to define those things because we don't even know what we mean when we talk about them related to ourselves. So you'll find that a lot of this is definitional, and that's unfortunate. But if you define things the right way, I mean, you can define thinking as what a human brain does, and then clearly computers don't think. So I just define computers out of thinking. And I can define computers out of intelligence by defining that right or wrong. So I think we have to set the definitions in a reasonable way, and when we do, we'll come to different conclusions. So I'm going to start, even though this is about artificial intelligence, I'm going to start with just a broad question. What is intelligence, and where did it come from? So what is it? I believe the best definition of intelligence I've ever seen, believe it or not, came from a Mormon apologist named Hugh Nibley, and he said that intelligence is defined as problem-solving ability. I've heard other people say something similar, but I love the way he said it, so I'm still quoting him even now. Intelligence is problem-solving ability. Well, that depends. What problem are we trying to solve? Well, it depends. It doesn't matter, but intelligence is solving a problem. So if you can solve a problem, it is intelligent. So you could ask a question like, is a calculator intelligent? Well, I can use a calculator to solve a problem, but does it go out and solve the problem itself? So what is the boundary between a tool and an actual piece of intelligence? That's one of the questions we have to wrestle with when we work on this problem. So where did natural intelligence come from, and what problem was it trying to solve? Well, we believe that life began through a process of evolution. And by the way, you notice all these pictures are AI generated. I tried to make as many of my slides with AI as I possibly could, specifically to illustrate the point of what we're doing here. We'll get to AI art in a little bit, but these pictures are all drawn by a computer. So where did natural intelligence come from? Well, let's see. First, it came from life. And life began with this process of what we call survival of the fittest or natural selection. But it begins at a very molecular level. In other words, certain molecules, we believe, if they can self-replicate, there'll be more of them in the environment than a molecule that can't self-replicate. And that is what causes life to begin. The reason I start there is because this means that molecules, just physical matter, properly organized, become alive. There is nothing magical about life. There's no difference between living matter and non-living matter except for its organization. It's organized in the right way, and then it self-replicates and eventually becomes alive. Then it needs to solve a problem. And you'll notice that intelligence is the sort of thing, and brains are the sort of thing that animals have, not plants. Why? Well, because animals move. And so moving is the problem that brains were designed to solve. So we have this beautiful thing called a neuron that evolves within multicellular animals. After the molecule, you get the cell, then you get the multicellular animal. Then within multicellular animals, you get movement, which means you have muscles. And you want to contract those muscles. This is one of the simplest animals around. This small worm has about 300, I think, something neurons. And what happens is it smells certain things, or it detects a bump into its nose. And if it does, its muscles contract differently. So it's a very simple reaction process. And the neuron's job is to take the sensor, the reaction, the sense that I noticed I ran into something, and move it to the muscles so that the muscles move and react to that sense. And to make this useful, these things they're just information transmission lines. Things go in the left side there of the neuron, they travel down the dendrite, and they go out the other side, and it sparks a muscle. So and it has to move as quickly as possible because you want to react quickly. Things that react quickly survive. Things that react slowly don't. So I've just invented a wire. And then you want to make more complex, maybe. You want to make more complex decisions based on the inputs you get. So some of these wires get hooked together not just as a line between the sense and the muscle, but they go to an intermediate stage where they connect to each other and they make more complex decisions. Like if several senses fire at the same time, then your muscles move this way. But if these other senses fire a different way, then your muscles move a different way. And what we have with this bundle of neurons is a brain. This is why brains exist. Now, evolution drives this whole thing, but it's important to know that evolution doesn't prefer complexity. Evolution doesn't have a goal to be complex. In fact, brains are expensive. Evolution likes to get rid of them. If you could survive just as well being stupid, evolution would be happier. But evolution creates intelligence anyway. Why? Well, because the majority of biomass on the earth is made up of bacteria, very simple things. But once that niche is filled with these simple things, then there is space for things to survive better by moving to a new niche. And to do that, it often will have to act in more intelligent ways than the simple life that's already filled. And so it will move into these new niches, and to survive in those new niches, it will create intelligence. So evolution creates a lot of really dumb things and one or two smart things. And as the space of the unintelligent positions are filled, then it creates intelligence at a cost to fill these new niches, and life spreads out into these new environments that require a certain amount of intelligence. So where did intelligence come from? Well, then where does it end? You end up with this being like you, like me, who can look up in the stars at the sky and say, what is this? Who am I? Why am I here? Where did I come from? And you can ask all those questions because of this process of evolution that came from the simplest of molecules all the way up to one of the most complex things we've ever seen in the universe, which is the human brain. So that's where that came from, and it's worth noting where it came from because it helps us decide questions like, can a computer be intelligent? Because what we've just decided is there's nothing magical about the brain. There's nothing magical about the human body. It operates through the laws of physics. And if consciousness can arise from a computer that we would call the human brain, then it can also arise maybe from other computational techniques. That brings us to artificial intelligence. And I'm going to start off my discussion of artificial intelligence with this challenging and slightly frightening, perhaps, quote by Irvin J. Good, a mathematician, fairly proficient and well-respected mathematician. He said, "Let an ultra-intelligent machine be defined as a machine that can far surpass all the intellectual activities of any man." So it's just definition, right? However clever. Since the design of machines is one of those intellectual activities, an ultra-intelligent machine could design even better machines. And there would then be unquestionably an intelligence explosion, and the intelligence of man would be left far behind. Thus, the first ultra-intelligent machine is the last invention that man need ever make. So I'm going to read that one again. the first ultra-intelligent machine is the last invention that man need ever make. So that's maybe the theme of my talk, is the last invention man may ever need make, provided, now notice how he finishes this sentence, it's very important and telling the way he words it, provided that the machine is docile enough to tell us how to keep it under control. Notice he doesn't say, provided we are smart enough to keep it under control. His entire assumption is that that is impossible. Once we create this thing, it becomes far more intelligent than us, and at that point, we are not smart enough to keep it under control. The question is whether it will be docile enough to let us keep it under control. And if we do, we will produce a world of unimaginable abundance that you cannot dream of. And if we fail, we will go extinct. And I believe that is true. So there's a lot of things that are important going on in the world right now. We probably underestimate the importance of this, because it may be the most important thing we do as a species and as a people, is to get this right. So what have we said? We said intelligence is a problem-solving ability. We can exist, and intelligence can exist when matter is properly organized. Evolution produces that proper organization. And the problem initially to be solved was reaction and movement, but it eventually advances to what we call general intelligence. And this is a phrase, general artificial intelligence is kind of a common phrase you will hear. But it will eventually advance to general intelligence, which then lets us look up at the stars and wonder why we're here and where we came from. That's natural intelligence. Artificial intelligence can be divided into two parts. What we call narrow AI, which is something designed to solve a single problem, and general AI, which is something that can adapt to whatever problems are presented to it in order to fulfill whatever goals you give it. So to cover that, there's so much to talk about. Right? This is the subject of dissertations and books and topics for. I could spend the rest of my life talking to you about this and barely scratch the surface of everything I want to say, and yet I have to fit this into about an hour or maybe 45 minutes. And so to try to make sense of this topic, I'm going to have to, I think to know where we're going, we have to know where we've been. So I'm going to give, as brief as possible, a history lesson on the history of artificial intelligence. I'm going to talk about recent advances, and then philosophical considerations, and then future implications for our society and the like. So, history. Early optimism. All the way back in 1943, these two people who I haven't heard, I don't know their names as well in the literature. For maybe that's my own ignorance, but they don't seem to be, maybe you know Kyle, but these names don't seem to pop up a lot. But they were the inventor of the art of artificial neurons called perceptrons. And what you do is you have an input and a desired output. And what you're trying to do is to find settings that will cause the input to go through this machine and give you the output you want. And you update the settings to get them closer and closer to the output you want. So what you do is you have a bunch of inputs. Maybe this is the height, weight, color of a rose. And the output is the species that you want. A number 1, 2, 3, which tells you which species it is. So you put the inputs up here, which are the different weights, colors, with the different weight, petal length of the rose, go in the left side. Each of those gets multiplied by a weight and added together, and what should come out is the color, or the species of the rose. This is an example of how you might use this to, and it's based on a neuron, right? Neurons have inputs and they have outputs, and they work roughly the same way. So these people are the ones who invented the perceptron, or the first artificial neural network. And what you're trying to do is, when you train a network, is learn the right weights to give you the right outputs. Now, I'm going to show you some of these algorithms. If you're not algorithmically predisposed, don't worry about it. Like, if this part, you can just shut off for those brief moments where I show you these algorithms. You can shut off and come back, and you won't really miss anything. But for those who kind of want to get an idea of what's going on under the hood, I'll show you just enough of these algorithms to kind of get a general idea. You want to train weights to get outputs that match examples that you have in the real world, or that you've produced for this thing, which is your training set. The first perceptron wasn't built until 1958, where this guy, whose name I do know, Frank Rosenblatt, built the world's first hardware implementation of a perceptron. And he had a little box of them where he could hook these artificial neurons together in long chains to try to get interesting behavior to come out of them. And they never worked very well, and he wasn't quite sure why they didn't work very well, but they didn't. At the same time, a guy named Alan Turing, which, by the way, if anyone has seen The Imitation Game, if you have not seen said movie, go watch The Imitation Game. It's a movie about the story of this man's life. He was gay. He was also probably autistic, and he spent his entire life struggling to imitate other people that he was not actually like. And it's a very moving story, and a lot of modern computing owes its existence to this very inspirational man. But he asked the question, can computers think? And he came to the conclusion, well, we don't know. And there's no way to tell. I mean, I can't tell whether you can think. So the only way I figure out that you can think is I ask you questions and you behave like you think, and then therefore you think. So he came up with this idea that if a computer behaves like it thinks, we have to conclude that it thinks. And he came up with this test to do so. You put a person in a computer room and you try to figure out if they're a male or female, and these days you try to figure out if it's a computer or a person. I mean, it's kind of the equivalent idea. His version was male or female. But he came up with this idea of a test that you would use to try to decide if a computer can actually think. So there was a great deal of optimism that we would be creating thinking machines in just a few years. And so we needed to be able to tell if they could think right away. Moore's law gave people a lot of optimism, and this was the idea that transistors shrink. Transistors are the things we make computers out of, and we were getting better and better at making them. And about every year to every 2 years, we would cut the size of a transistor in half. And when you do that, you put twice as many transistors on each computer chip. And because the electrons don't have as far to travel, you could turn up the speed. And so these things got faster and smaller and bigger, more transistors on a chip. And so computing power essentially was increasing on this exponential path. We'll talk about the power of exponentials in a little while. But if you're familiar with nuclear bombs, they go boom because of the power of exponentials. Exponentials surprise you. If I take a number 1 and I double it, you get 2, then 4, then 8, then 16. And in 30 steps, you get 1 billion. And the next step, you get 2 billion, and then 4 billion. And then in 60 steps, you get 1 billion billion. And so things that double surprise you. And that's how we got from a computer that filled a room to a computer that fits in my pocket and is 1,000,000 times more powerful and 1,000 million times cheaper, and yet it fits in my pocket. Moore's law. So the beginning of artificial intelligence was filled with hype, it was filled with optimism, and it didn't work. And so, so this is the idea that Moore's law has continued. This was his original drawing of it, but it has continued to the present day, basically. I skipped this one. This guy's Noam Chomsky. He began this idea of natural language and machine translation. They were short. They had a summer project where they were going to solve computer vision in a summer project, and then they were going to figure out how to translate things from computers. And the Defense Department was really interested in this because they wanted to be able to translate Russian documents quickly so that they could help our spies, right? And so we needed to translate Russian, and he thought a computer could easily do that. All you have to do is take all the words, look them up in the dictionary, and put English words there, and you could translate Russian, right? And the famous example is the spirit is willing, but the flesh is weak, and his computer algorithm spat back the vodka is good, but the meat is rotten. And the problem here is that translation, you almost have to understand the sentence before you can translate it. You have to understand the idiom, you have to understand the sentence, and you have to know what the words mean so that you can disambiguate them. And until you know what they mean, you can't do this. And so we found out that computer translation is mind-numbingly difficult. And again, he thought he was going to solve this in a few years, and it didn't work out. This created what we call the AI winter. The hype led to disillusionment when it didn't come to pass, and disillusionment led to loss of funding, which led to even less things coming to pass, which led to more disillusionment, which led to even less funding, and AI just kind of disappeared. This is in 1964, the National Research Council became concerned about the lack of progress and formed the Automatic Language Processing Advisory Committee, or the ALPAC, we love our acronyms, to look into the problem, and they concluded in a famous 1966 report that machine translation was more expensive, less accurate, and slower than human translation. Which is crazy, right? Less accurate, slower. It's easier to pay a person to do this than to get a computer to do it. And after spending some $70 million, the NRC ended all support and funding. Then we have the Lighthill report. In 1973, there's a Professor James Lighthill who wrote a similar report for the UK Parliament, and it ended all funding for artificial intelligence in the UK. Worse, a book came out by Marvin Minsky and Seymour A. Papert. And Marvin Minsky, by the way, is one of the founders of artificial intelligence, machine learning, very famous guy, brilliant researcher. And he wrote a book about perceptrons, and he basically said they don't work. They can't separate any information that isn't linearly separable. In other words, if I can't draw a line and everything on that side of the line is a rose and everything on that side of the line is an iris, I can't tell the difference between roses and irises. If you need any more complex function than that, you can't do it with a perceptron. It doesn't work. And if you stack perceptrons together in funny ways, it still doesn't work. And so this killed all work in neural networks, together with all the work in expert systems and machine translation. And so artificial intelligence, as a buzzword, basically died. People were still doing research, though, sneakily. They would give it other names. Machine translate, they maybe wouldn't call it artificial intelligence, they'd call it machine learning or something like this. But research continued just under other names, but there was a lot less funding for this sort of thing. Eventually, we got some recovery happening in the 80s. NavLab was one of the first kind of people to go back to this work, and they tried to make a self-driving car, and didn't work very well, but it went about half a mile an hour, but it could kind of keep from hitting things most of the time. It was a big van because the computers that ran it filled the entire van. But this was back in the 80s, and this was, Carnegie Mellon was a big hotspot for machine learning, and this is when things started to pick up again. 1985 is when neural networks came back onto the stage. And what happened was, and again, details are not important, but for those of you who are interested, the short version of it is someone figured out how to stack perceptrons together and change the activation function. In other words, how you sum them up. You sum all the inputs and you create an output. Well, if you have a nonlinear function in there and you sum them up and add the output, you can get nonlinear outputs out of big networks with hidden layers, meaning layers in the middle. You can stack them together and you can get arbitrarily complex functions out of these things, which means if this function can be fit, a neural network with enough nodes can fit it now. Now the trick is, you now have to figure out how to update all those weights. The perceptron was simple. Once you stack them together, it's kind of complicated to figure out how to update these weights, especially since the function is going through this nonlinear sigmoid function thing. And what he figured out is you can actually, what the backpropagation algorithm figured out is that you can take these partial derivatives and you can pass them back through this thing. And all that really means is if I have an input and an output and they don't match, I can figure out which weights are causing them not to match, and I can push the weights towards a match. And if I put an input and an output and they do match, I can figure out which weights are making them match, and I can push those higher to make it more likely to match. So if I randomize the weights, I now have a way to learn the right weights until I match the function. And this, they discovered, can match basically arbitrarily complex functions. So now we have a general purpose function approximation technique with a way of learning the weights. This brings up the question, can a computer learn? Well, again, it's a definitional thing. If it improves performance when presented with examples, it learns. That's what learning means. It's what humans do when they learn, and it means the computer can learn. So let's stop. We need to begin with this whole thing. Computers only do what they're told. It's not true. Computers can learn, and they can come up with answers their creator never dreamed of. So I, as a creator, can build one of these neural networks, and it can find a solution to a problem that I never dreamed of. All I have to do is give it inputs and outputs that I want it to match, and it finds a way to match them. Even if I don't know a way to match them, it can figure it out. Because the computer can learn, and it can learn things that I, as its creator, myself did not know if I have training data. And that's what this algorithm enabled. In 1984, we had another big step forward. And again, this may not look like artificial intelligence, but it's really important. That's when the World Wide Web kind of began to explode. And it exploded exponentially as people put more and more text on the internet. What you will discover, or what we will say, is that neural network function can learn any function if it has enough data. And the internet gave us a near infinite amount of data. Pictures, words, sentences, discussions, papers, books, all of it gets put on the internet, and a computer can crawl that whole thing, read the whole thing, and use it as its training data. And so the internet is a huge input to neural networks and to machine learning in general. Without the internet, we wouldn't have things like AI art and the rest. In 1997, a computer first beat the world grandmaster at chess, Deep Blue versus Garry Kasparov, and the world began to change quickly. This is a graph of the best chess programs ranking, and you'll notice from about 2005 on, computers outrank every human who's ever played the game. And so no human can now play chess as well as a computer. Now, the way these computer things worked is they would search. By the way, one of the things that happened is as soon as computers, originally, chess was considered like the epitome of intelligence. And as soon as a computer could do it, well, that's not intelligence. That's just searching. The computer searches through all the solutions, finds the best one. That's not intelligence, right? And so as soon as computers succeeded at these tasks, they got delegated to non-intelligent tasks. This is just computation. Well, the thing is, to do really well at chess, you have to search, and they can search the options better than a person. But you also have to evaluate the quality of the position you reach at the end of the search, because you can't search all the way to the end. There's too many positions. So what you do is you have to look at a position and say, who's going to win that game? And you can do it really simply by saying who has the most pieces, weight the queen more than the bishop, whatever you want. But that's not quite right, because a pawn that's one square away is suddenly very powerful, one square away from being queened. So what you really have to do is take a position and then look at who won the game later on. And then that's your input, the position, and the output is who won the game. And suddenly you can do something like give that to a neural network, and it's supposed to learn what makes a good position compared to what makes a bad position, so that it can search ahead and then rank all the positions it reaches at the end, right? So there is intelligence involved in assessing those positions. And these best chess programs do this first by sucking down every grandmaster game ever played and using that as their training set. And then you can't get better than people that way, but you can start playing yourself. And they did, and they played themselves, and they played themselves, and the more they played themselves, they created training sets, and the better they got, the better the training sets got at assessing the position, because the right person would then win if you're really good, right? And then you know whether a position is good or not, and so you get the better the program, the better the training set, the better the training set, the better the program, and computers very quickly became better than any human on the planet. And this is important because it's a pattern we will see later on. Computers very quickly overtake people in individual tasks. But the people don't stop doing the task. People still play chess. They just use the computers to help them get better. People are now better at chess than they ever were because they have computers as their teachers. And people didn't stop playing chess because of that. I think that's important when we look at AI art and whether people are going to stop doing art because when computers become better at us at drawing pictures. Are we going to stop drawing pictures? No, we're going to draw pictures because we love it. And the computer may help us draw better pictures. Right? So this is a theme we'll see again and again. In 2005, we finally got a car that could drive itself reasonably well. We still don't have them, generally purposed on the road. This was the DARPA challenge where this computer drove through the desert. It's much smaller. It's not a bus anymore. We still don't have them on the road today, but one of the reasons for that is we're afraid of getting sued. Right? If you build a computer and it drives the car and it kills somebody, and you knew that there was a problem, the computer wasn't perfect. You knew it wasn't perfect. So you didn't fix it and you released it and somebody died. Now you're liable for their death. You could be sued. The problem is computers are better than people, or they're at least very close to being better than people at drive. People are really bad at driving. We fall asleep. Computers don't lose their attention. They don't text on their phone. They don't get drunk. And so I believe we're very close to or not past a point where not only can computers drive cars, they can probably do it better than us. And if we were to deploy artificially intelligent cars in their imperfect state right now, we would save more lives than we would kill. But we would kill a lot of people because the computers would be imperfect. but we would also save more lives than we killed. And we have to find a way as a society to assess when we push that button and we say, we're going to let our computers drive our cars. How many more people do you have to save before rather than kill? How good do they have to be before you accept them as a driver? Do they just have to be better than a person, or do they have to be perfect? Because if they have to be perfect, they're never going to get there, because we're not there. Right? All right, so anyway, cars. 2005 is when we started getting cars that could drive. Although I admit the DARPA challenge was driving through the desert, not a busy street with kids jumping out. But they've gotten better since then, too. Something really weird happened in 2005, though. Remember how I said when you shrank processors, the clock speed went up because things were closer together, so you could make the computer run faster? In 2005, that stopped happening. And what happened was, if they turned the clock speed up any farther, when they got really small, a lot of heat leaks out of the transistor, and it gets hot. And the smaller you make it, the more of that heat leaks, and the hotter it gets. And if you turn up its clock speed to make the computer run faster, it melts. And so around 2005, computers stopped getting faster, believe it or not, in a single processor. And it just so happens that around 2006, people liked playing computer games. And this thing called the GPU, or graphical processing unit, what it really is it's a card that you put in the back of your computer, which is a second sort of brain. The main brain does things one at a time. It's called the central processing unit. And computers were built on central processing units from the days of von Neumann and Turing all the way till now. And suddenly, in 2006, we got these graphical processing units. And what those were built to do is to take, I got to keep my slides linked. Here, I'm just so I can read them is here, but it's not control. I got to keep them together. This is what you should have been looking at. And what happens is, if you're playing a computer game, let's say you're playing a first-person shooter, and you've got a gun and you're trying to shoot the guy down the hall, right? You trace the light down the hall and you bounce it off all the things in the hallway, and it creates a realistic-looking image that you can use for your computer game. So these things were not built for artificial intelligence. They were built for computer games. And without computer games, there would have been no pressure, or not the same pressure, to make this change, to build these GPUs. And the GPU works very differently than the CPU because it wants to trace every ray of light at the same time. So they're like really slow computers, but a billion of them, a trillion of them that all work at once and trace every ray of light down the screen to help you make this image of your computer game. And GPUs started getting exponentially faster about the same time that computers stopped getting faster. And so what I would call this is the rise of parallelization. Two things happened. We started putting multiple CPUs on the same chip, and then we started building these GPUs, and someone looked at the GPU and came up with a brilliant idea, which I still am not sure I perfectly understand, where he said, I can take this GPU that's designed to trace rays of light, and I can use it to update the weights of a neural network. And the same math does both. And so I can hack this GPU that was never built for this and use it to do something it was never built for, specifically store and train neural networks. And so this was a huge leap forward. I still remember this moment. In 2011, Watson beat the world's best player at Jeopardy. And I remember, because my research had been in machine learning for language, natural language processing. We were trying to do part of speech tagging of these ancient texts because we needed tagged examples so that the computer could train on parts of speech. It needed to know this word in this context was this part of speech. And we wanted to learn that in a machine learning sense. But we needed trained examples. So we were hand training all these examples in these ancient languages to then give them to the computer. And I knew how hard natural language processing was. And what really impressed me about Watson's competition with Ken Jennings et al. Is that it understood language spoken in a natural way. And it could answer questions about it. It could figure out what the question was getting at and find the answer. And that allowed it to win at Jeopardy. And I remember sitting in my in-laws' home and hearing about this and saying, the world just changed. And I knew it was going to take a while to become kind of broadly available and general purpose, but I knew that the world was changing and that this was a big kind of moment. So, the rise of artificial neural networks. There were a couple initial problems with these neural networks. Too many nodes meant it was too computationally intense and complex to use, and too many nodes meant that it had a lot of power to represent complicated functions, but then it would do what we call overfit. This is going to be important when we talk about copyright. But overfit basically means memorizing. You can think of it that way. Let's say I want to tell the difference between red dots and blue dots, but let's say there's some noise along the boundary. If I memorize the training set, the green line gets every single example right in my training data. But then when I give it real data, it will make more mistakes than the black line. The black line will get more things right than the green line because the green line is overfitting the noise. And it's doing that by memorizing the training examples. It's memorizing things that have nothing to do with the actual thing it's trying to learn. This is noise, and it's learned the noise. If you memorize the training example, you don't generalize well to new things you've never seen before. So you need more training examples than you have this is not an exact rule, but this is the concept. You need more training examples than you have nodes in your network. And what does that do? It forces the computer to compress. In other words, to understand. You see, memorization is not understanding. Understanding is finding patterns. And if the computer has less nodes than there are training examples, it can't memorize the training examples. It can, but I'm oversimplifying. But it has to find some compression of the data. It has to find patterns in the data, and it has to understand the data. That's what we mean, I think, by understanding, is we have simplified rules that solve complex problems. We understand, we simplify, we compress. And so overfit was a big deal. So how did we solve this overfit problem? Too many nodes can be solved through the GPUs, and too much overfit can be solved by massive amounts of data. So you have enough data, you can make something that's complex enough to learn really complicated problems without overfitting. You just have to have a lot of data to do it. And the internet gave us that. So this is where things became exciting. And this is what we called the deep neural networks. And this is where we started to see human-level performance on things like image classification. Is this a picture of a cat or a dog? Is this a picture of a lion or a spaceship? You could give these computers pictures, and it would tell you what it's looking at. And it could do that because we gave it these vast amounts of images from the internet. And there were several forms these took: convolutional neural networks, recurrent neural networks, adversarial neural networks. Convolutional neural networks are based on kind of how the human eye works, so no wonder they do a good job of figuring out what things are. Recurrent neural networks, though, are these networks where they kind of point back at themselves. They're notoriously difficult to train, but they have the advantage that they can look at time steps. Because at time 1, I go this far through the network, then I feed back into myself. The network at time 1 is now the input to the network at time 2. I feed back on myself. And you keep track of time by going through the network more than one time. This was also notoriously difficult to train, and it had the problem that you couldn't really do it in parallel because you had to do it one pass through the network at a time, and it made it less parallelizable. And then we had these adversarial neural networks, which is basically where I train one neural network to make a picture of a cat. I train another neural network to tell the difference between computer-generated cats and real pictures of cats. And I train these two neural networks at the same time. So what happens is I train the one network to learn to generate pictures of cats, and whenever the other network catches it, it has to update its weights because it failed in generating realistic pictures of cats. Whenever the other network fails, the detection network, whenever it fails to detect an artificial picture, its weights get updated because it's not as good at telling the difference between a computer-generated and a real cat. And when you train them together, and you have both a network that detects AI-generated art and another network that generates AI art, and they fight each other trying to get better. That's called an adversarial neural network. And this was the state of the art till about 2017. And they did really well at computer recognition, sort of okay at computer translation, and sort of okay at image generation. But the real advance started happening around 2017. And this is when we start to get human-level performance on all sorts of tasks like handwritten recognition, speech recognition, image recognition, reading comprehension, and natural language understanding. And by the way they're testing this level and how they create the human level is they give people problems on Ataturk, which is this thing where you pay people to solve problems for you. And a lot of people will solve them poorly because they're in a hurry and they just want to get their $2. But you give people $2 for answering surveys, kind of. That creates this human-level performance, and then you want to see if the AI can do better than that. Well, humans can actually do better than that if they try, because a lot of people on Ataturk aren't trying. But nevertheless, this is interesting. We're beating humans when humans aren't trying very hard on a lot of problems. And it happens around 2017, you'll notice. And that's because December 7th, or 6th of December, 2017, was what I would call kind of the breakthrough. And it was a paper called Attention is All You Need. It was written by researchers in Google and the University of Toronto. And it was basically this paper that proposed what we call the transformer. And I almost wanted to put a picture of Optimus Prime. Some of you probably don't even know that what I'm referencing there, but transformers, right? Autobots, rage there, okay, yeah. And again, I've got the picture of the network architecture on the left. I don't expect you to know what all that is, and it doesn't matter. And frankly, there's a lot of it I don't understand. I'm getting better at it, by the way, Kyle. So, but the basic idea here is you have a layer of the network whose job is to figure out which inputs matter for your output. So it basically figures out which parts to pay attention to. So you start with a transformer that transforms your data, and this gets rid of the recurrence. You don't have any recurrence. You take all your data, you transform it into a single layer that has all the information in it. You feed it to your network after going through this transformer that moves it into this new space. The network figures out which parts to pay attention to answer the next part. And then another layer of the network figures out what the answer should be given the attention that it should be paying. And you separate out this learning of attention and this learning of the answer into these different layers of the network. And so it's not anything really different than what we've seen. It's still backpropagation. It's no longer convolutional, it's no longer adversarial, and it's no longer recurrent, but it is just a backpropagation neural network that has layers of a specific kind stacked up in a specific way. And why they called it attention is all you need is they found that they didn't need any of those other pieces. They could throw them out and get better results with self-attention, positional encoding with no recurrence, and semi-supervised learning. That was the other big advance, because remember before, I needed to go through and label all the parts of speech so that I could give my computer examples to learn. Well, this doesn't do that anymore. It takes unlabeled data and figures out how to learn on unlabeled data. It's called semi-supervised learning. Let me give you 3 examples and you'll see how the semi-supervised learning works, how you might create some training data from stuff on the internet. A language model. Autocomplete on your phone is a language model. So you've probably seen it. It's the thing when you're typing on your phone that predicts what you're trying to type. And all it's really doing is predicting the probability of the next word, given the previous N words and maybe the first letter that you've already typed. So if I type N, it figures out what the most likely word is. That's a language model. And all it does is it's read the internet and figured out the probability of the next word given the 3 previous words, or the 2 previous words, or the 4 previous words. That's it. And it produces text like this. This is randomly generated on my phone. You can call me today. I was thinking about what you might want to stop the Nazis in a while. You are feeling better soon as well. It just doesn't work very well. Then we have these large language models, and they're semi-supervised. And what they do is they take the entire context, maybe of an entire paper, and then they take out a word and they kind of say, what's the probability of that word given the context of the entire rest of the paper? And the attention layer figures out which other words are most important for figuring out what that word is. And then the other layer says, okay, given this attention and this context, this is the most likely word that fits in this hole. So all you have to do is read the internet, take a few words out, and use that as your training data. Predict the word I took out from the context of all the words around it. That's it. No hand labeling, nothing. And it learns to speak like a human in the context of the conversation it's having. And this is where we finally got human-level machine translation. This is what DARPA was trying to do all those years ago. This is what those reports said couldn't be done. And now it's happening, and it translates the flesh is willing, but the spirit is willing, but the flesh is weak. It translates it right. Because it's got the context, because it's got the attention, because it's got the massive amounts of training data just sucked down from the web. And then how do you use the same idea to make pictures? Well, let's say I have a picture of a cat, and somebody maybe has posted this cat to Facebook, and they've labeled it as a cat. So I know it's a cat, and I've got this picture of a cat, and I want to train one of these networks to learn how to draw pictures of cats, not recognize cats. Convolutional networks already sort of do that. We want to draw a cat. So what we do is we put some noise over the top of the cat, and then we start at the end with all the noise, and we say, what noise would you have to remove? It works backwards, and it's just because computers seem to be really bad at removing noise, but they're really good at adding noise. And so really what you do is you say, what noise would I have to add and then once it figures out what noise was added, then it knows how to subtract it. You add the noise, and then you subtract it off after. But I'm going to talk about it in backwards because it's easier to understand. If I start with all the noise all the way to the right, I can ask the question, what noise would you want to remove from that image to make it look like a cat? In the context that it was a cat. Well, because I started with a cat and added the noise myself, I know what noise should be removed because I'm the one that added the noise. So I know what noise should be removed. So I can train the neural network to pick the noise that should be removed to give you a cat. But you'll notice in the image kind of 1 from the right, I could also have said in the context that that's a bunny, and you would have gotten a very different image. Correct? And so by learning what noise to add or remove in the context of a prompt, it learns how to draw pictures of cats and bunnies. And it does that from training examples that it's pulled from the internet. Again, how this works is really important for questions of copyright that are going to come up in a minute. Is it copying the cat? Well, the training example was the cat, but when I ask it to draw a cat, it doesn't have enough nodes to memorize every pixel of cats. It has to learn something about the ideal cat. In other words, it didn't overfit. It didn't memorize the training set. It learned what cats are. It learned what cats look like, and it learned how to draw a cat. And I can say, draw a line image of a cat, and it will do it. I can say, draw a photorealistic picture of a cat, and it will do it. And I can say, draw a cat like it was painted by Escher, and it will do it. And I can say, draw a cat that looks like something, let's see, what's the name of the guy who did Starry Night? Van Gogh, thank you. I draw a picture of a cat that looks like Van Gogh, and it may never have seen a cat drawn by Van Gogh, or even in the style of Van Gogh, anywhere on the internet, but it has seen cats before, and it has seen images that look kind of like Van Gogh, and it can put them together, and it knows how to put those styles together with the parts of a cat and give you a picture of a Van Gogh cat. And it didn't do that by memorizing or copying things on the internet. It did it by understanding the pictures it was looking at on the internet. And this is how you create a training set without labels, right? You still need the it's a cat, right? So, present advances. We are now living in an age where computers can write music, they can make art, they can process and understand natural language, and then the question is, have we reached this stage of artificial general intelligence where the computer can look up at the sky and say, who am I? Where did I come from? Why am I here? By the way, go ask ChatGPT where it came from, why it's here. It's kind of an interesting conversation. So let's talk about each of those. AI music. For free AI music, I did some Google searches. I'm showing you the result of some Google searches. 4 AI music tools, generators that create unique songs to use in your projects. So it used to be that if I wanted to have a song track for my YouTube channel, I'd have to pay somebody to do that for me. And now I can ask this thing to do it for me, and I can give it the style of music I want, and it will write me music that is unlike any other song on the internet, and it'll create the music for me in any style or beat or speed or whatever I can specify. And I can specify those things with natural language. And it's because of these transformers and these latent models, latent generative AI models that allow us to do this with music We get the same thing with AI art. There's several of them on the market right now. Stable Diffusion, DALL-E, and Midjourney. DALL-E is done by OpenAI and is owned by Microsoft, so it's part of Microsoft Bing. If you go to Microsoft Bing, switch to chat, then switch to the creative version of chat, and they say, draw me a picture of, it'll spit your prompt back to DALL-E and give you a picture, which is where I got most of my pictures from this. Stable Diffusion is open source. You can download the weights. You don't want to download the training examples and train it on your computer. It basically ate the internet. But you can download the weights. The weights are about 5 gigabytes. And I can run them on my home PC. And it will spit out images. So some of the images here I created on my desktop computer with Stable Diffusion. Midjourney is probably the best, but it is not free. They'll give you like 20 free images, and then after that, they make you pay for each image you make. But once you pay for it, you can use it in commercial products or whatever you want. So here's some fun ones I asked Bing. I asked Bing for Unitarian Universalism. For its concept of Unitarian Universalism with a flaming chalice, and this is what it drew. I really like this. This is my favorite Unitarian Universalist chalice I've ever seen. And by the way, each of these, it actually generated 4, and I picked the best one because some of them are bad. Some of them are good. And the way it does this, of course, is it starts with a random noise field. Is it creative? Yes. It starts with a random noise field, and it starts removing noise to make it more like whatever things you put into your text prompt. Here's another one, Unitarian Universalism with a flaming chalice and galaxies and nebulae in the background. I think that one was fun. I wish the chalice was, you could see the whole chalice. I struggled for a while to give it a prompt that would make it show the whole chalice, but it kept cutting off parts of it. How about an airbrush painting of a beautiful woman in a dress with flower print, lace, ruffles, ribbon, bow, include face, and please don't have, lowers, errors, cropped waist, quality, ugly duplicate, morbid, mutilated, blah, blah, blah. Don't put anything not safe for work, right? You put all that stuff in the negative prompts at the bottom. And you get this picture of a beautiful airbrush painting of a woman. This one's really fun. Please give me a photograph of Johnny Depp in a flower print dress with lace ruffles, ribbon, and a bow, and include the face. So there's Johnny Depp I promise Johnny Depp never dressed that way, in exactly that way at least, although he dresses in funny and interesting ways. Here's another one generated with the same prompt. It put the flowers in the background. It does have flower print on his suit. He got a flower print suit out of that one. This one's fun too. But there's lots of ways to make Johnny Depp into a flower print person with the flowers in their hair. But maybe you really wish Johnny Depp had been the one who played Batman, so you want to know what that would look like. Here's Johnny Depp as Batman. It's pretty good. I did these on my computer. These are all Stable Diffusion run on my desktop. So let's move on to ChatGPT. This is a language model now. And it's the same idea as the image, only this time, I take a word out and it learns the new word, right? This is the autocomplete on steroids. But let me show you how different it is than autocomplete on steroids. Can you write me a romantic letter from me to my wife for our 20th wedding anniversary, which is next month? So here, my wife gets her wedding anniversary letter a little bit early. She's sitting in the audience. ChatGPT, of course. I'd be happy to help you write a romantic letter to your wife for your 20th. It's very peppy. For her 20th wedding anniversary. Here's a sample letter that you can use as a starting point. Please don't just use it. Use it as a starting point. It's very diplomatic about that, right? My dearest wife, wife's name. Think about this for just a minute. An AI wrote this. Think about it. This is crazy. This is absolutely insane. My dearest wife, as I sit down to write this letter to you on our 20th wedding anniversary, I can hardly believe how time has flown by. It feels like only yesterday that we exchanged vows and promised to spend the rest of our lives together. Not only is its grammar impeccable, it's saying the right things. And yet, here we are 2 decades later, still standing strong and more in love than ever before. I'm going to read this whole thing because it is impressive. I'm sorry. If you want to skip, I get it, but I'm going to read the whole thing. I want to take this opportunity to tell you how much you mean to me. You are the love of my life, my partner, my best friend, and my soulmate. I am so grateful for every moment that we've shared together, for every laugh, every tear, every triumph, and every challenge that we've faced as a team. People buy Hallmark cards for this, right? And people don't get offended when the Hallmark card gets the right feeling. This gets the right feeling, and it's a Hallmark card. This is how I feel about her. Through thick and thin, you have always been there for me. You supported me in my dreams, encouraged me in my struggles, and lifted me up when I've fallen down. You have a heart of gold, a spirit that shines bright, and a love that knows no bounds. As I look back on our journey together, I am filled with awe and wonder at all that we've accomplished. We've built a beautiful life, a wonderful family, and a love that endures. We've weathered storms and come out stronger on the other side. We've laughed and loved and grown together in ways that I could never have imagined. And yet, despite all that we've achieved, I know that there's still so much more to come. This letter has structure, and it's ending on the future. It knew to put the future stuff at the end and the past stuff at the beginning and the current stuff in the middle. It went from past, current to future. Did you notice this? There's still so much more to come, and I'm excited to continue exploring the world with you and experience new adventures, to create new memories, and to love you more deeply every day. Thank you for being my wife, my partner, my soulmate. Thank you for the past 20 years. Here's to many more to come. And it knew 20 years, because I said 20th wedding anniversary. So in that context, it knew that we've been together for a long time. It wrote a different letter, because if I told it 1 year, it would have talked about the beginning of our journey and stuff. It knew to talk about it this way, from all that context, with all my heart, me. Now, can you please rewrite the above letter, but this time as if it was from the Book of Mormon? Now, I don't know how many of you have read the Book of Mormon, so this may not be as funny to you as it is to me, but this is priceless. Not only is it priceless, it's right. Like, this is what the Book of Mormon sounds like, okay? So, and I did this to show that it understands. And I remember a few years ago, I was talking to one of my friends who's an AI researcher still. You know, I moved on to these other things, and he's still focused on AI. And I asked him what he was doing these days, and he said he got an internship to work with NVIDIA. Not an internship. What is it when? Yeah, but it's a sabbatical to leave the university and to go work with NVIDIA on deep language models, large language models. And I asked him why he was doing that, and he says, because this is it. These things understand. If you ask them to talk about Hillary Clinton, they start talking about pro-choice stuff. If you ask them to talk about somebody from Texas, they'll talk about pro-life stuff, and it knows. It knows enough about these people and their politics to write the right sort of politics for them, and to talk like they talk, and to write like they write. It understands all this stuff, and it didn't memorize it. It learned it, and it learned because it doesn't have enough nodes to memorize it. It learned it. It learned the patterns, and it gained understanding. And the understanding is somehow buried in all these nodes. And this is a great example because it shows that it knows what sort of writing the Book of Mormon should be, and it can't look up the Book of Mormon to write this. It doesn't have access to the internet. Somewhere buried in its neural network is an understanding of Book of Mormon-ish text, right? So listen to this. Write me the above letter, and the above letter, by the way, it knew the above, so went to the above letter, looked at the above letter, that was part of its context, rewrote it now with the Book of Mormon as extra context. ChatGPT certainly here's a revised version of the letter written in a language that might be found in the Book of Mormon. We've always interacted with computers with programming languages. This is the first time you can talk to a computer. It knows what you're saying, and it responds to you appropriately. I don't know if I can express how mind-boggling this is. My beloved wife's name, as I take up my stylus to pen this epistle unto thee on the occasion of our 20th year of matrimony, verily I am filled with gratitude and joy. It seemeth but a fleeting moment since we were joined together in the bonds of holy wedlock, and yet lo, 2 decades have passed in the blink of an eye. Isn't this wonderful? This is the most amazing thing I think I've ever read. And by the way, I'm not going to read all of this one, but I'll leave it up here. If you guys want to read it, you can. If you're watching online, especially, you can pause it and read this. But notice it suddenly is talking about children. The original version didn't say anything about children, but Mormons have lots of kids. So in the context of the Book of Mormon, suddenly it's chatting about our children. It's changed what topics it covers. It's changed how it talks about them. It is amazing. And there's a glimmer of understanding here in what it's saying. So here's some news articles I pulled. I just did some random ones. Here's one. The newest version of ChatGPT passed the U.S. medical licensing exam with flying colors. This thing can pass the medical licensing exam, and it can It can has better clinical judgment than many doctors. It can diagnose your diseases. So if you're a doctor, your job is at risk. We're going to talk about jobs in a minute, but if you're an artist, your job is at risk. If you're a musician, your job is at risk. If you're a truck driver, your job is at risk. Even if you're a doctor, your job is at risk. If you're a programmer like me, my job is at risk because this thing can write code. I can ask it to write computer code, and it'll do it. ChatGPT 5 release date, claims of artificial general intelligence. Remember we talked about specific intelligence, like I can play chess, and general intelligence, like I can solve any problem you give me if I have enough time and resources. Respectable researchers are starting to talk about ChatGPT in the context of general artificial intelligence, especially the new versions that are still coming out. Here's another article on that idea. So what does all that mean for our philosophical and social implications? Let's chat about copyright for just a minute. Obviously, artists are really angry. One of the things they will say with some basis is, I didn't give you permission to take my picture of a cat and use it to train this thing to draw pictures of cats, so people no longer want to pay me to draw pictures of cats. Now they just get them for free. And I didn't give you permission to use my picture of a cat that way. Fair enough. That's a very reasonable argument. They've got a point. It will not stop the creation of AI art. Adobe is already building AI art projects based entirely on things without copyright encumbrance that is in their library that they've built up over years. It's not as good because it can't suck down the whole internet, but it'll just make them a little worse. And they're only going to be a little worse for a little while. That's the other thing to remember. And so challenges to these AI art on the basis of copyright, even if they're successful legally, will not stop the production of AI art. The other problem they have is that I already have Stable Diffusion sitting on my desktop. It's not like they can take it away from me. It's an open source program. I've got the weights sitting on my desktop. Even if somebody rules that the person who trained that network violated copyright, they still can't take that thing away from me. It's sitting there on my desktop. But I think the other thing to bring up here is what we talked about in terms of understanding versus memorization. If I look at pictures on the internet and learn how to draw whatever I want to draw, and I draw a transformative image, that is protected. And you cannot claim copyright when I do that, if a human does it. Right? If a human looks at thousands of images of pictures, whenever you put out a picture, you're allowing me to train my brain, neural network, on what beautiful art looks like. You consent to that whenever you let me look at your picture. In fact, you can't let me look at your picture without doing that. The problem is that they're thinking of the computer differently than they're thinking of my brain, right? Because they're thinking the computer just memorizes and spits things back out. So the computer is copying me, but a human brain is maybe being inspired by me. But I think our brains work a lot more like these AI art generators than we realize. And if you're going to tell me that a computer can't look at a picture and learn how to draw other pictures that are transformative from that picture, then you're also telling me that I can't look at that picture and be inspired by it. And that's a problem for these copyright challenges, if we understand AI as it really is. Which of these pictures was generated by AI? You can tell if you really pay attention. It's the one on the left, and you can tell because their fingers aren't right. These AI things don't. Oh, am I on the wrong? You should have been looking at this the whole time. This is the problem when I have this screen and that screen and they're not synced. The one on the middle and the one on the right are both real. The one on the left is AI generated. By the way, do you recognize her? That's our Hermione from Harry Potter. Yeah. Famous actress. I put that image after generating it with Stable Diffusion. I asked it to draw me a picture of Emma Watson in a flower print dress. I was into flower print dresses because I just done Johnny Depp. So then I said Emma Watson in a flower print dress. And you notice it did Emma Watson a lot differently than it did Johnny Depp. But anyway, it's the same prompt. I just changed Johnny Depp to Emma Watson. And this is the picture I got. You notice it put the flowers in the background instead of just on her dress. It picked up on flower print and put flowers everywhere. I put that image then back into Google reverse image search. And I said, find the most similar images out on the web like this. And those are those two on the right. Those are the most similar images on the web. The AI may well have been trained on those two images, but you'll notice the image it drew looked nothing like those. Those are just the most similar ones. This is transformative. This is not memorization. This is not copying. This is a transformative, creative, new work of art, unlike anything that had been created in the past. And so that, again, is a challenge for these copyright claims. And thus, the question of, it may have trained on their artwork, but it didn't memorize them, and it generated its own thing. And you can tell that it didn't memorize because it doesn't have enough nodes to memorize all the images that were fed into it as training data. So, in fact, you don't want it to memorize. If it memorizes, it doesn't do as well when you give it a prompt it's never seen before. Generalization requires understanding rather than memorization. For anyone who's really interested in this topic, I really recommend watching Everything is a Remix by Kirby Ferguson. It's 10 years old, but it is classic. Everyone should watch this. It's a YouTube video. Kirby Ferguson, Everything is a Remix. If you have any questions about kind of the issues with copyright law and how it, we built copyright law because we wanted consumers to have access to beautiful art. For consumers to have access to beautiful art, you have to pay artists. Or at least you used to. And in as much as I feel bad for the people who are losing their jobs, what we're really talking about is artificial scarcity. We're going to artificially create scarcity so these people can keep their jobs doing things that a computer can do better. Not yet, maybe. Human artists are still better than the computers. But for how long? Are they going to stay better 10 years from now than the computer? At what point do we say it's no longer, it's like chess? And remember, those chess algorithms, they learned to play chess. They started out by sucking in all the grandmaster games. Did the grandmasters consent for their games to be used to train a neural network? Anyway, everything is a remix. Creativity, if we ask the question, can a computer be creative? Creativity is the process of taking things you've seen before and mixing them up in a new way. And that's exactly what this computer is doing. So yes, computers can be creative. Yes, these things are creative. Yes, they are transformative. Moving along to the scary part of this, I don't know if you realize what Facebook is doing, but if you use Facebook, it reads everything you write. And it builds up an AI model of you. And it is not interested in making you happy. It is interested in making sure you stay engaged with the site so they can sell advertising. If their site was a subscription, if you paid to use Facebook, they might care about your happiness because then you would keep paying them. But they don't. They care about selling you advertising hours, and that means keeping you engaged on the site. So what they do is they build up a voodoo, this is a very creepy image, but they build up an artificially intelligent voodoo doll of you, and they learn how to poke that doll to keep you engaged. And you know what engages most people? Anger, frustration, outrage, political polarization. You can make an argument that this sort of thing is on the brink of kind of destroying the world already. And it's doing so by polarizing us, by keeping us engaged, and it is artificial intelligence. That's what's happening at the core. A good text on the subject. He's got other things he says that I don't agree with, but he's got a good point here. This is Harry Johanan, Stolen Focus, Why You Can't Pay Attention and How to Think Deeply Again. And his comment is, this is a systemic problem because their incentives are misaligned with our goals as users of these products. Google, Facebook, Microsoft, they all do this. And it's part of this advertising-driven model that misaligns their incentives with ours. Jobs, we've kind of covered this as we went, but these things are coming for your jobs. So we have a choice. Do we move to a world of artificial scarcity to preserve those jobs? Or do we move to a world where we allow the computers to do the production for us? If you add these intelligent machines to robotic means of production, they can produce things for us. They can produce the goods and services we want for us. But when we do that, we will no longer have jobs to do. That's going to be a traumatic transition, and we are standing at the brink of it right now. We have to pay attention to it. And it may be that something like a universal basic income that is paid by the production of these AIs is the only real solution. But if we don't do that right, if the people who bake the AIs keep all the money, then we're going to have a problem societally and it's not going to be good for these rich people either, because no one can buy the things they make if they don't have jobs. And if they make all the money and that money isn't distributed in some way, there's no one to buy things for them, and the whole economy, them included, goes down. So we have to find a way to navigate a future without work. We're not there yet. This is looking forward, right? I'm not claiming that computers can do all of our jobs, but I'm claiming we're close. And it's coming, and we need to kind of prepare and be ready for it. The future of artificial intelligence. I'm going to do this really quickly, but I want you to get an idea of, remember what I said at the beginning about exponential progress? What I did here is I estimated about how much computational power it would take to simulate your entire brain, and then I plotted the world's fastest supercomputer every year against that. And if exponential, and I did it on a logarithmic scale, and so that means a linear trend in this logarithmic space is actually exponential. And that last little bit is huge. This is the part of a logarithmic scale. To make that last little step is to make it 10 times faster than it currently is. On the other hand, if you double every 2 years, if you just kind of track that trend up, it should happen within this decade. You'll cross that line. That doesn't mean we'll have computers that are every bit as smart as us, because we still have to figure out some of the algorithmic problems, and we can't just simulate a brain. We don't know the right map. We don't know how each different neuron, some neurons dampen things, some neurons excite things. We don't understand all that yet, and we don't have a good map of a human brain to simulate. But the point is, you have the computational complexity and the computational power to do it if you wanted to. And the reason we're starting to see computers that can do things like talk like a human now is because we're approaching the computational power necessary to simulate an entire human brain. And in this case, I think what we're really doing is simulating the language center in the left hemisphere of the brain. We're doing something very similar to what our language hemisphere does. We just need to now connect it to all the other parts of our brain, to the visual cortex, to the hippocampus, right? But we've got this kind of language model. If you damage the language model, people still have thoughts, but they don't put them into words. So what ChatGPT is doing is you give it general thoughts as the context, it puts them into words. Humans have a part of their brain that does exactly that. I have this thought, I'm trying to convey it to you, and I just kind of open my mouth, and I have this almost unconscious piece of my brain that sits and churns on it and spits out words that match my thoughts. I think that part of my brain is basically ChatGPT, and we've duplicated the capability of that part of our brain. We need the rest to make truly conscious, intelligent, sentient computers. And it's coming, is kind of where I'm headed with this. And in fact, not only is it coming, it's more frightening than that. Within the century, the world's fastest supercomputer will not only be able to simulate your brain, but every brain of every human being on the planet. If trends continue. They may not. At any point, we could fall off of this kind of Moore's Law hype train. In fact, Moore's Law is certain to end because we can no longer make processors smaller because you're hitting the quantum limits. Heisenberg's uncertainty principle, you just can't make things any smaller. But we're still making them. Now we're working with parallelism and these graphics processors, and that is allowing this process to continue. And if it does, for another 50 years, not only will the computer be smarter than you, it'll be smarter than every human who's ever lived within the century, if the trend continues. I want to help you wrap your head around kind of how big a deal this is. This is my point of the power of exponential. I put 1 grain of rice on one thing of a chessboard, 2, 4, 6, 8. By the time I put doubling each square, by the time I fill up this chessboard, I can take these grains of rice, stack them end to end, and go from here to Alpha Centauri and back 4 times. That's how much rice fits on a chessboard. That's how many doubling you need to get from 1 grain of rice to enough rice to go to Alpha Centauri and back 4 times. It's really hard to wrap your brain around what exponential progress does. Let me talk briefly about another application. It is Easter. I have to bring this in. This is my mother. She died in 2009. I have journals and videos and writings of hers. Imagine if I took ChatGPT, fed them, just like I said, write as if you were in the Book of Mormon. What if I fed them all of her writing and said, please respond to me as if you're my mother, in the context of everything she's ever written that I'm able to get my hands on? You may not think that's resurrection, and it may not be. It may not be her. It certainly wouldn't be if all I had is ChatGPT, but if I had all the other parts of a human brain in there too, it might be her after a traumatic brain injury where she's forgotten some of the things. But even if you think it's not, this is a sort of either really creepy or really beautiful memorial to people who have died. And we could do that sort of now. It's a little tricky because ChatGPT won't give me their weights to train on. I have to go through their API, and it's difficult. I've been working on seeing if I can figure out how to do this, but we're almost there now, where you could, and this would mean a lot to me because, and I know, who she was won't be able to see this, but the last time I talked to my mother, she had to go, or I had to go, I'm sorry. I was late for something, and I was kind of short with her. I told her I loved her, but I had to go, and she wanted to talk, and I didn't sit around and talk to her. And 2 days later, she was dead. I would give a lot just to be able to say goodbye. So I want to give you the idea, I'm going to end with the quote I started with, that this could be beautiful. It could be a beautiful future of abundance, of resurrection, of cheap doctors, cheap healthcare that does a better job than our current set of doctors. Or it could be a nightmare. It really could be a nightmare. And it depends on sort of how we start out. Let me give you an idea of how hard this is. This is called the alignment problem. Let's assume that I would really like to create a vacuum, but I want it to be generally intelligent. Because I don't want it to just be a Roomba that drives around and vacuums my car. I want it to figure out the best way to vacuum my house. So I give it the goal of having a clean house. And I tell it to solve that goal any way it sees fit, because I'd really like to have a clean house. Generally intelligent, simply set goal. Give me a clean house. Solution? I'm sure you can come up with a couple. Kill every human to make sure they stop tracking dirt into the yard and live for all eternity in a clean house. But it doesn't really align with what we wanted when we wanted a clean house. It is incredibly difficult to give our goals to these machines such that they really do align with our goals. So I've already mentioned a few movies and TV shows like The Imitation Game. You should really watch iRobot. It's a movie about a goal, about some robots that were given a goal. And it decided the best way to achieve the goal sounded really good, like the 3 laws of robotics, what we want to do to make humans safe and happy. And it decided the best way to achieve that goal is to enslave all the humans, right? But that really wasn't our goal. What we really want is a flourishing life. Right? The alignment problem is incredibly difficult. And we have to kind of get the alignment problem right to make the future the beautiful one I suggested instead of the scary one. And I don't know how to do that, which is either exciting as a research opportunity or terrifying. Take your pick. So does anyone have, I've spent a lot of time talking, but I'm happy to answer questions. I mean, I could talk about this for a long time. There's a lot more I can say, but yeah.
So yeah, if anyone does want to talk, I have lots of thoughts myself.
Please share.
Because I'm also in tech too, and I honestly don't know where to start.
Neither did I. That was part of the problem. There's too much.
I've got like a half dozen. All right, I'll say the one that I'm least worried about is actually the art question.